Alright, so let's go on to, now let's see, do I want, oh yeah, I did want to take another set of data because I tweaked the decay rate. So this, what happens is this, pumping cuff here, as I said, it does have the button, but it has this little screw, and you can change how fast the air bleeds out. So this button is, well, this button is here if you want to use a stethoscope. But I have this cuff here, and we're going to use that to get the high quality measurement. But you can see, well, you can't see here because we don't have the graph yet. So get yourselves back to the BP data, to Dr. H01 here. And I've already set up this stuff for you. Excuse me. Okay. So I want to take, yeah, with the new decay rate, where, here it is. Okay. So, nope. I want to get this out of here. Yeah. Okay, so I have the recording conditions set, I think. Yep. Alright. And let's delete these runs. Okay. Alright. And just bring this back to 0. And of course I undid this thing. So let's see if I can get it back on. And put this here so you guys can see me. I've been doing this all week without help. Because now it's not going to cooperate, huh? Well, I'll just put it on loosely here and see if I guessed right. No, I did not. Okay. A little looser. And that'll work. Okay. So let's do a measurement. Oops. Oops, I goofed. So, FYI, I've decided the best measurement rate is, in fact, 50 hertz. I think 40 hertz would work, but we're here just to learn about it, not to actually get it completely right. Alright, let's try one more time. I just didn't want to have, at 100 hertz, there's just so much data to deal with. Beautiful. left arm very steady. Yeah, you can see where I started talking. You don't want to talk because it can feel those vibrations. Okay. And let's use my little cuff here to get the what we'll call our accepted value, if you will. Well, we need a way to judge our technique. Oops. The battery finally died. Oh, no, I got more. Yeah, the battery could be dead. There we go. Oof, that's a high number, maybe because I'm talking so much. Okay, I'm going to write this down. So this thing says, holy crap, my systolic is 166, my diastolic is 119, and my heart rate is 70. Oof, which isn't bad, but normally in non-pandemic conditions, I work out quite a bit, so my heart rate's usually about 60. I'm going to do it one more time. Yeah, basically the same. Okay, let's see what this thing tells us when we get there. Alright, so I need to export this data. This is run number 1. And I just want the time and the cuff pressure. Yeah, this thing has an algorithm to try to tell you what the systolic and diastolic is, but it doesn't work very well. Okay, export the file. And yeah, this is another thing that's tricky. I have to figure, oh, not Google Drive. I have to figure out why this thing makes those tables. So what we're going to have to do is put this into its own file. Now let's see, this is, yeah, you can see these exports. I took Jenny's, my wife's blood pressure, and I took my son's. And that's going to be part of your homework. So this is Dr. H 2021 0326. So normally I would just import this into a spreadsheet that I was working on, but then it gets all screwy. So I'll show you what to do. Maybe this is taking too much time, I guess. I don't know. I wanted to do this. You know what? We are taking too much time. Let's just get into it. I'm going to study that myself. Alright, so let's get back to this. Here we go. We have data I took the other day. And so the very first thing we can do is let's make the a graph that we made earlier. So insert chart. We want it. So we've decided now that we're happy with the sampling rate. So instead of dots with straight lines, we're just going to pick the straight lines. Curved lines are tempting, but they could hide artifacts, meaning we want to show the world that we're not afraid to use straight lines, so no one will doubt our selection of data rate. The straight lines would hide those things, but I mean the curved lines up here, but we don't want to do that. We want to use straight lines. So there it is. And unfortunately I've already culled this data, but when you do it for your assignment for the checkpoint, you'll see I have ooh, what's this? I showed some people stuff. Okay, good. Right, this is where I show the data quality, but I already showed that to you. And there's another blood pressure measurement of mine, and then my son, and oh, there's the finished product. So, oh well, I didn't notice this, but I changed this, so I wouldn't just simply say, oh, I already have it. I would encourage you to create this all like we're doing right now. Excuse me. So I plotted the data. I did the culling. I got rid of the points in the beginning I didn't like. And the way you do this is just say shift up. You see you lose some stuff there, but I don't want to do that here because I've already done it. We don't want to lose information. Okay, now we are going to excuse me, we're going to use a trend line, which I don't generally like to do, but I'll explain why we're going to use the trend line. I usually get mad at students that use trend lines. And if they keep doing it, I take points off of their labs, because I want you to do the fits the way we learned how to do fits. So we're going to insert we've got the chart highlighted, and we're going to insert a trend line, and we want more trend line options. And we want to go over here to the right now, and we have choices, and we're going to pick the polynomial. And remember, we are going to do a fourth order polynomial. And we're going to say display equation on the chart. There it is. And because we need these numbers. And let's see, I want to format the trend line, not the label. Format the trend line. There we go. So, why did we decide on 4? First of all, a first order is simply, oh, it won't even go lower than that. So this is sort of like x to the 0 power and x to the 1 power. Oh, x squared. So this is actually a third order polynomial, huh? They call it a second order. So we look at the coefficient of the highest order term, in this case the x squared, and we see that it's 0.1769, and it's too big, and also the line doesn't fit the data very well. So now let's pick a third order. It fits better, but see, it doesn't fit well. And we go up to a fourth order, okay. And it's fitting good, and the leading coefficient is quite small. So let's try a fifth order. And we notice that with the fifth order, it's really quite small. 3 times 10 to the minus 5. And yeah, this could be helpful, but we go back to here. This is 3 times 10 to the minus 4. Yeah, and the next one, 3 times 10 to the minus 5. We could use this one, maybe. Let's try one more. And we'll see that the coefficient of the, the coefficient of the sixth order term is really tiny. So there's really no reason to use that. So just in the interest of keeping it simple, really, we're going to stick with the fourth order. I see why they call it that, because 4 is here. Okay. It does mean 5 terms, though, because you have to include the zero order term. So the reason we did that is to get an idea of how many orders we need. Because it turns out, I did the experiment, the trend line doesn't do that great of a job. I mean, it does an okay job, but it's not as good as we need it to be. So what we're going to do is we're going to take these numbers and we're going to type it into here. So the first one is 0.00, in my case, and it should be the same for you, 3. Then it's 0.0366. Oh, it's minus too. I forgot the minus sign. Make sure you're careful. Get the signs in there. Then the second order is 1.5151. Okay. And the next one is minus 31.311. And then the zeroth order term is 355.24. Okay, so now we have all of the polynomial coefficients into our table there. Are you fully deflating before? Yeah, I was. Yeah. Wow, that's very good, Alexander. That's correct. You have to make sure that you do that. I think it's because it stresses out your arm. I don't think because you wouldn't be able to get it on if it was high enough to squeeze the vessels closed. But I did notice that when I took the multiple readings earlier to show you the data rate, I was pushing the button to make sure it was deflated, because I was noticing before class that it was definitely throwing things off. Good. So Alexander asked about, am I fully deflating, right? Yeah. Oh, okay, I guess you guys can each see this chat. Well, if you type it into everyone, everybody can see it. But if you type it in only to me, not everybody can see it. Again, because I'm moving the chat window onto my shared screen, but apparently you guys can't see it. Okay. All right, so what do we do next? Well, we need to make our fit line here. So this one is a little tedious. Again, my logbook is in the way of my keyboard. So, equals the fourth order coefficient. Don't forget we need dollar signs, so that would be the F4 key. Times, and in this case the X is the time. and this is to the fourth power, plus the next coefficient, and again we need dollar signs, so you can either hit the F4 key or just click inside here and add the dollar signs. Times the time, and now cube to the third power, plus the second order coefficient, dollar signs, times the time, now it's squared, plus the first order coefficient, F4, times the time to the 1 power. You don't have to type to the 1 power, but that's just itself, plus the 0th order coefficient, and if we want to be real pedantic, the time raised to the 0th power, which is just 1. And not bad, huh? 181.8, 184. So then, I don't know of any shortcut for this. We just now drag it down and fill it in. And if you pull it lower and lower, it goes faster and faster. And again, it used to shoot past too, but there, it slowed down. Great. And I'm gonna just format that right while it's all selected. Yep, 2 decimal places. And we have equals get the residuals, the data, minus the fit. And we might as well just do the residuals squared right away, equals the residuals squared. In fact, we could have done all 3 of them. So we'd only have to do this once. There we go. Nice. Well, let's get rid of that. Okay, so what can we do? Well, we can add the fit line into here, and we can let's see, select data. So I'll show you a little trick. So the series name is the fit. And so what about the X values? So I can just select a few of them, and then I can go down here and see what's the last row. And come on, 1216. So then I just go here and I changed the 7 to 12.16. Sweet, huh? So now I don't have to drag all the way down. And then the same thing here. Just select a few points and change this to 12.16. And yeah, you see the trend line didn't work out too well. I don't know why, but it's not a problem. And so I'm going to format that to fit, and we don't want any marker. None, it already has that. Okay. And then the line. Oh no, this is not, this is the line, the border of the marker. So we want a solid line. Yes, yes, we know. And we'll make it red. I like making fit lines red. Okay. We're on the way. Let's insert a legend so we can make it easy to keep track of things. And well, that's neat. It puts the trend line in there too. And now here's an advantage: when you instead of typing in a name, you pick a box for the name. So we can change it to fit line, and it changes in the legend. So we need to clean up the fit line, huh? Now why is it? I just want to make sure I didn't make a mistake. N6, that's the... Did I get this? Oh, here's where I made a mistake. No, the sign are in there. I don't have to put it into the equation. Okay. Let's just... that's not going to make a difference. Well, let's just see. Yeah, it didn't make any difference. I didn't think it would. Okay, so, of course, we have to now make our sum of the residuals squared equals sum, and I can play the same trick as I did before. We know it's got to go to 12.16. And that number is big. It does, at the moment, doesn't fit. That's why it turns into pound symbols. Okay, so I better pause here. Does anybody want to see equations again, or some part of this again? Alright, good job, guys. Yeah, I think you've learned to slap me and say, yo, hold up. Alright, so another thing. I don't know if we've done this part. Have we done this part about solver and data analysis? Have we ever seen this before? We've seen it in Google Sheet, but have we seen it here? When you go to the data tab, everybody sees analysis and solver. That's what silence tells me. Alright, so we go to solver, and we want it to minimize the sum of the residuals squared, and we want it to vary our coefficients. And I forgot to say this. What we've done here, and it's an important step, we did the trend line, number one, to get a feel for the number of the order of the polynomial. But the other thing we've done is it's called we've seeded the fit. Now we did it earlier, and I don't know if I said it to you. We put in some slope and y-intercept. For a straight line fit, it's not that critical. But for a fourth order polynomial fit, it's really critical to give the solver starting numbers, or it could get lost. It may still get lost, we'll see. So let's hit the solve. Oops, it's taking its time. It's flashing. Why is it flashing? Ah, it got an answer. Ooh, how's that, huh? Isn't that amazing? And I don't think it changed these. Oh, you can't go back with the solve. You can't hit the back button. So isn't that killer? Now, here's what's really sweet. We need to subtract the background. Well, the fit line, well, in our case, yeah, it's sort of a background. It's the average pressure. It's the pressure, the base pressure in the cuff. And so we want to subtract that out so that we can see just the wiggles. And so, well, lo and behold, that's the fit line is the fit, is that. Oh yeah, what I was going to say is, when I tried to come up with a fitting equation, and the first thing I thought of, excuse me, and I just realized I can write on the spreadsheet now. I figured out how to do that. So the first thing that came to mind was the ideal gas law, PV equals nRT. This is the Rydberg constant. And so we have temperature, pressure, volume, and this is basically the number of moles. So it's basically the amount of excuse me, it's the amount of molecules of gas. So I'm thinking, oh, okay, I have pressure, and I have on I can make a fit because I can figure out what's the rate that the air is escaping. The problem is the cuff is not rigid, so both the pressure and the volume are changing. So that's when I realized I couldn't come up with a simple fit equation. And in fact, I might be able to make a polynomial fit somehow using coefficients for pressure and volume, but because I was only interpolating, I said I can just use the polynomial fit. So anyways, we can do our background subtraction, and it's already got the table for us right here. So what we're going to do now is we're going to take time, and we're going to hold down the control key, and we're going to select the column with the residuals. And we are going to insert, once again, just with straight lines. And this is going to look kind of funky, but never fear. The way to clean this up is just to change the limits here. So we're going to say, we're going to make it -10 because there's definitely a little bit of waviness in there. So that's suggesting to us that we should have probably used the next degree. We should have done a fifth order polynomial. And how cool is that, huh? This is just the greatest thing. I'm so proud of myself. And so let's first of all, and I guess we could zoom this a little bit, huh? Could make this a 5, right? And then maybe 33. So this could be bigger. Let's say 7. There we go. And then, of course, there's this way of stretching it. So this is pretty darn cool, huh? And you see how we lose the bottom on the right. Now these waves are throwing us off. And the fit works. There's also the idea that maybe you limit the sum of the residuals squared to just a certain area too. That's all but at the physics 1200 level, this is already pretty darn cool. So basically, what you get, one thing, like I said, you can still see a little bit of waviness here. So if I was doing this for real, I would go back and I would go to a fifth order polynomial. So let's add some other stuff to our main graph. So we want to make some horizontal lines. And so we were told that, oh, I didn't tell you. Give me a minute. I wrote down the blood pressure here. Wow, same as what I just measured. Must be because I'm talking so much. So it says here that my 165 and 111, whoops, and we don't know, okay, heart rate, well, we're just going to put some times in here for the time being, and you'll see what we'll do with these. 10, 15, and then we want to do the delta, so that equals this minus that, and then the frequency is equal to 1, and the delta t is the period. I'll explain that in a moment. Equals 1 divided by this, and so then beats per minute, BPM, is going to, well, let's say we'll put that, it's going to be heart rate. We want to multiply the beats per second times 60, right? Equals this times 60, and that's beats per minute, BPM. Okay, so I just typed in a couple numbers that I from the cuff. I had 165 over 111. I just put in two random numbers here, and I made the difference between them. Then I took I took 1 over the difference. What's the time? We're almost out of time. We're almost done. And then and that would tell me if I know the time, the two times of a certain. I'll show you on the graph. We'd get beats per second, but I want beats per minute. So then I take that and I multiply it by 60 to get beats per minute. So this is also beats per second. And how we do that, just in case you don't know what a period is and such. If I have any kind of wave and I have time, so the time between a repeat is called the period. So that could also be here and here. So that says the seconds per one cycle. So if we want frequency, frequency is cycles per second. So we just do 1 over the period, which is 1 over seconds per cycle, and that gets us our cycles per second. Okay, so this isn't quite so hard. So we need horizontal lines that are going to stretch all the way across the graph. So we need from 0 to 35. So we just put a 0 here, 35 here, and then this is going to equal the number we typed in for systolic, equals here, and we're not going to fill in, but if I put the $sign here, then I can just do this. And then I ought to do this equals the diastolic. F4. Then I can drag it here. And now we need time are going to be vertical bars. So I need to see so it goes from 0 to 200. So I should be able to get away with this. 0. Oh no, excuse me. This is not. Sorry. This is the x-axis. So this equals T1 F4. This is equals to the T2 F4. And then I can just drag these two down. And now I need y values for those. And it's going from 0 to 200 looks good enough. It seems strange, but if I tell it to be a line, it'll just form a line between those points. Okay, so now we need to add to this graph. Select data, but this will go much faster. So new. So this is going to be my systolic, and the x values are here. The y values are here. There's one horizontal line, see? Then I need to add the other one. So this is diastolic, and it's the same x values as the systolic, and the y values are those. Pretty nifty, huh? Now we want to add the vertical lines. So this is going to be T1. Now we just got to be a little careful. The x values are going to be these two. And Y value are going to be 0 to 200. So we should get, yep, there's our first vertical line. And we just got to add in the last one, T2. And X values are here. And Y values are there. Nifty, huh? Now you might consider putting these into the other graph as well. So let's see. So it said 165. So let's look at what's going on up here. So this means we need to go to, say, the 5 to 10 range. What's the time? Oh, we have to go over the report. And let's zoom in. This is 8.5. No, sorry. So maybe I don't like 10. Let's make this 20, or like 15. And now, of course, well, we shouldn't bother moving that yet till we see the full extent. And we want to go, say, 100 to 200 here. Right? 100, yeah, let's put 200 here. So, well, not bad, huh? So it's basically when your heart is just able to get, it's always going to pulsate, but when that blip appears, that means now it's forced open that blood vessel. So now it's expanding even a bit more. So that's the point between 9 and 10. So let's take a look at the residuals. Basically, you're going to get the systolic from the main graph. And so it looks like this one here. But one could argue for here as well. But this could be, let's see, that's 8.8 seconds. This is, if you hover over a point, this is 9.7 seconds. And we picked, alright, we can now use our time, 8.8. Let's make this 8.8. Aha, that's up here. So we're picking more like down here, which is closer to 10. So you can see, and then we need to go to go beyond this. So there, it's a toss-up between those two, right? Now, let's see. Heart rate. What you do for heart rate is you move the vertical lines to two different bumps. The horizontal, the vertical lines. And I would suggest you do that several times, so you can get some kind of average. And I can spend more time talking about that, but I want to get, for people who have to get out of here in a few minutes. And so it said the low pressure diastolic is down here, and that is at about, well, it's doing the trend line. So let's see, this is 17 seconds. 17. Okay, so about around the 17-second range. Oops. So that is right about here. See, me personally, I would pick this point as the diastolic. because even though we're getting a little bit of wave, I noticed that the lower part is not getting as low anymore. So I would argue for this point here, and this is where you might consider putting the vertical lines on here. This is at 19.3 seconds, okay. So we can get a closer look at it on the big graph. Okay, so then you might zoom in. So for your checkpoint work, which will be, I'll set it all for that Sunday, you're to go through and analyze these other sets of data. Now here's a tip. You've done all this work to create this framework here, right? So here's what I would suggest you do. Go here to the bottom, move or copy, and we want to create a copy, and we want to move it right after Jenny, so before Dr. H number 2, and we're going to rename this to Jenny, and we're going to, all you need to do now is delete out all of these points. Yep. And you just clear contents. You go here, copy, and paste up here, paste, and now you just got to tweak everything. But you've got a lot less work to do now. Okay. So I wanted you guys, because I would suggest that you start working on the report, and of course I am recording this, because the next part won't take very long. Okay. So for the checkpoint, you already know the data rate set study and the 3 data sets in addition to the one we did together. Extract the blood pressure and the heart rate, and I've written down what the cuff told me, and I'll tell you that when we see each other again. So for the report. So we studied BP and EKG for our report. That's sort of in the introduction. So for a blood pressure, you basically, it's correct cough, I think, not Korotzoff. But we used this decaying pressure graph. And then you talk about the ideal shape and how our transducer we can't just simply pump up to the average pressure. We can't find some magic place where we could just see the shape. So our transducer can't do that. So we did our plot, and we did and this is for a report. You have to go into more detail in your notebook. So we did a polynomial fit. We used a trend line to get seed numbers. We did a polynomial fit to get our average pressure, a line for average pressure. And also we should add in here the data quality. We subtracted out. We only took the data on only the decaying pressure points. So we used this interpolated technique. We did a polynomial fit. We used the trend line to give us seed numbers. Then we used to put into the solver. The solver gave us a very nice fit. And then we subtracted the fit line from the data points. And then we used this graph to tell us where we think is the low pressure. The high pressure was just where you first started seeing it. And yeah, ideal shape, the greatest negative swing is the diastolic. And I've already done this work for you, the ability to add in the horizontal and vertical lines. Okay. And then we can add some more detail. I'm just suggesting. I'm not going to ask you to hand in a report, but I would say this will also guide you in your checkpoint logbooks. So you have a week and a half to do your check. You're gonna in your. I don't expect you to have written down every single thing we did today. I just hope you wrote in your like a diary entry. Oh, first we did this, then we did that. But I don't expect you to have written down the whole interpolative technique. But I do expect to see it in your checkpoint notebook. Okay, look at that, 125. Any questions?
Will this video be posted up in Canvas?
Yes, I'll get this up. Well, it'll be in YouTube, and I'll put a link. And I will put this slides I'll put up tomorrow or Sunday. And I also gave you this data quality. I made some screenshots on Monday to help you, to remind you about the data quality. Because we only want the part where the pressure is decaying. Any other questions? Right, so there won't be any Zoom recording now. I've got this recorded here on my local computer. So I'll get this up on YouTube as soon as I can. I'm losing my voice. Any other questions? Okay, I'll stop this.